I'm back with the rest of section 11, or some more of it at least. I think I've got enough time to get all the way through it. So where I left off was I was going to do this example here, which is kind of like the lab that goes with section 11. What you have in the lab is there's what amounts to a little tray with water in it. And there's a plastic bar that vibrates up and down and makes waves. And you look at what the waves do when you do different things to them. And it is kind of the same thing here, except I was just trying to make it a little more colorful than a little plastic bar in a tray on a table somewhere. I said this is a log floating in a river or a pond or something, and there's this lumberjack who recently cut down the log and he's jumping up and down on it. Anyhow, based on the information that's given here, we are supposed to find what I mean by the displacement is how far above or below equilibrium this point is. Okay, how far is it displaced from where it would be if you just had calm level water? That's y in that equation, y equals a sine of all the rest of that stuff. So we want the displacement of point P at this particular time. And so basically what it is filling numbers into that general equation that I mentioned a moment ago. And what a lot of the work is figuring out what those numbers ought to be. So I'll just pick you up and put you at the other end of the table down here. Okay, so it doesn't matter what order I do things in here. Maybe I should just write this down to begin with. That should be in your notes from the previous recording, the first part of section 11. And y is what the question is asking for. How far is the water level displaced from its equilibrium position? X is where you are along the surface of the pond. T is what time is it. The phase angle, it says that the lumberjack jumps on the log at t equals 0. Okay, so at t equals 0, the log has not been displaced from equilibrium. Okay, the log is at x equals 0, and when he jumps on the log, it's t equals 0, and so you'll be taking the sign of 0, which makes the displacement 0, if the phase angle is 0. So anyhow, that's my excuse for getting rid of the phase angle. The question says that the log begins to bounce at t equals 0. At t equals 0, it is not displaced. Well, we need, in no particular order, we need the wave number. The amplitude is given, okay? If you look at the picture, it shows, it's labeled right on the picture, that from the center line to one of the peaks is 20 centimeters. So we've got a number all queued up to go in for A already. We need something for K. K is 2 pi over lambda. So maybe I should start by getting the wavelength. wavelength is the speed divided by the frequency. We're told that these waves move at 4 meters per second. For the frequency, says the guy is hopping at a frequency of 1.25 hertz, which is pretty rapid. This guy's been drinking some coffee, I think. That's fairly rapid. He's kind of excited. Anyhow, you divide those and you get a wavelength of 3.2 meters. So this symbol K stands for 2 pi over lambda. And this part you can look up on the formula sheet. This expression here, that one you're supposed to know. That's pretty basic to the understanding of waves. It's kind of like if you don't know F equals ma, you don't really know anything about mechanics. And if you don't know V equals F times lambda, you don't really know anything about waves. And so those types of things I leave off of the formula sheet, but I'm just about certain that you can look this one up on there, the 2 pi over lambda. And that comes out 1.96. Maybe I'll fill the unit in. The unit on this would be meters to the -1 power, because you see the 2 pi is dimensionless and the wavelength is in meters down there in the denominator. So you get 1 over meters, or you could call it radians per meter if you like the sound of that better. Rolls off the tongue a little nicer maybe. We also need something for the angular frequency. Omega is 2 pi f. And the frequency again was given in the question. So you multiply and that comes out about 7.85 seconds to the -1 power, radians per second in other words. So I don't really need to write it down this way to answer the question, but just to kind of look at it and admire it for a moment. This sort of thing is often called a wave function because it completely describes the wave, okay? At any place, at any time, this tells you where the surface of the water is. So throughout space and time, this completely describes the wave, not only telling you the water level everywhere and every time, but you could take the derivative of this function, which would give you the velocity of the water's surface as it vibrates at any place at any time, or you could take the second derivative and that would give you the acceleration. And basically everything there is to know about the wave can be derived from its wave function one way or another. A wave function becomes a very important concept if you get into quantum mechanics. Some of you may take the third part of this course, Physics 133, during the spring semester. And if you do, you will definitely hear the phrase wave function again. So anyhow, this is the general function for the wave, but we're interested in what it gives for y at a particular place and time. I should probably, yeah, that's going to show up, I guess. So the picture shows that the point we're interested in is 10 meters from the log, or the location of the vibrating log seemed like a convenient place to call the origin. And the question says we're interested in this particular time. So you fill all that in and then push a few buttons. We've got y equals the amplitude, 20 centimeters. I probably should shift this over a little bit. And as I'm sure you've noticed by now, I don't generally fill in the units on every single intermediate step when I'm solving a problem, but let's fill them all in here just so you see how they work. 1.96 meters to the minus 1 for the wave number, and then x is 10 meters. So you see meters divided by meters cancels out, and you're left with a dimensionless number here. Creeping over toward the edge of my picture. Omega is in radians per second times 5 seconds. So seconds over seconds cancels. Seconds over seconds cancels here. And this is a dimensionless number. And be sure you're in radian mode. For last week's lab, lab number 10, there's usually somebody that gets caught by that. They come up to the front desk and it's like, why is my graph coming out almost a horizontal line? Did you have your calculator in radian mode? No. Try again. So avoid that pitfall. So at this particular moment, the water level is 14 point, this particular moment at this particular point, the water level is 14.4 centimeters below where it would be if there was no wave disturbing it. Time to flip the page over. I believe what's next is a discussion of the speed of various types of waves. Yes. And I'll point the camera over there in a moment, but basically what the first line or two says is that the speed of a wave, now this is idealized textbook waves, okay? You know, just like I've said before, an introductory course like this one is full of frictionless surfaces and massless rods and all sorts of things like that that are approximately true sometimes, but you know, if taken literally, would be kind of silly. And this is another example of the same thing. If the restoring force for the wave is precisely linear, okay, then what it says there is true. In the real world, well, for example, there would be no such thing as rainbows if you took this exactly at face value. But what it says is that the wave's speed depends on the medium, not properties of the wave. Waves of different frequencies and amplitudes have about the same speed. In other words, say that you're standing on one side of a very large field, and you've got a couple of friends a mile away on the other side of this very large field, and both of your friends have a whistle. One is a high-pitched whistle and one is a low-pitched whistle. Both of your friends start blowing their whistles at the same time. Now, to get from where they are to where you are at the speed of sound takes about 5 seconds. Okay? The speed of sound is not actually particularly fast. Well, it depends on what you're comparing it to, I suppose. But that's the reason, for example, that during a thunderstorm, you see the flash of lightning, and then a few seconds later, you hear the rumble, the thunder. The flash from the lightning comes at you at the speed of light, which, while finite, I'll put in another plug for taking the third course. That's one of the labs we do in Physics 133, is we'll measure the speed of light. But it's fast, it's seriously fast. So over short distances, the light gets to you nearly instantaneously. The thunder, on the other hand, comes to you at the speed of sound, 5 seconds for every mile. So you can figure out how far away the lightning bolt was just by counting off the seconds. If it's 10 seconds, it was 2 miles away. Anyhow, back to the point here, which is that if both of those sounds that have very different frequencies leave their sources at the same time, over here on the other side of the field, you will hear both sounds arrive where you are at the same time, okay? The frequency is a property of the wave, and it does not significantly affect the speed that the wave travels. What does affect the speed of sound is what medium it's traveling through. I just happen to have some numbers written in here. The speed of sound in air, as we've already seen, is somewhere around 340 meters per second. And, you know, it varies a little bit depending on exactly what the temperature is. On the other hand, if you're designing a sonar system, the speed of sound in water is 1,480 meters per second, which is more than 4 times faster. And, you know, other materials have their own speed of sound as well. The speed of sound in helium is significantly faster than the speed of sound in air, even though they're both gases. So the speed of sound does not depend on properties of the sound itself, like its pitch or its loudness, but it does depend, well, there are 2 different labs that neither one of them for Physics 131, but there are 2 different labs that we do in here where we measure the speed of sound. One of them we use sound that's a few hundred hertz, and the other one is ultrasound, which is 40,000 hertz, and the answer comes out the same, okay? It's the same speed of sound, even though the frequency differs by 2 orders of magnitude.
Well, here I am all of a sudden in an entirely different place, looking at a somewhat different version of the notes, the note packet, I'm holding the camera in my hand. My apologies if I'm making you a little seasick or something like that, but the recording you were watching I made a year ago, and I afterward started thinking it got a little long-winded in places, and I could redo a few parts. It'd be a little better. So I've taken a different approach here to deriving the speed of a wave on a string. So what we've got here is a pulse moving along a string, like, sorry about the tilt, that's better. So it's like there's a long garden hose laying on the ground, and you pick up one end of it and you give it a flip, and it creates this pulse that travels along the hose. That's a good example because the waves go nice and slow instead of hundreds of miles an hour like on a guitar string. So the idea is these drawings are made from the point of view of somebody who is running alongside of that pulse, and you're keeping it right next to you so that the wave is drifted a little bit. That looks better. The wave is basically stationary relative to you, the observer. And if you want to consider a little piece of the string or hose or whatever you want to call it, seen from that point of view, it's in, as it passes over the top anyhow, it's basically in uniform circular motion. I mean, other parts over here are headed in other directions, but that little chunk right there at the moment is moving as if it were kind of going around like that. And so therefore the net force on it has to equal mv squared over r, as we saw earlier in the course. Well, that force toward the center comes from the tension in the string, as illustrated in the picture on the right that shows the components. The piece of string on this side, this is a close-up of our little chunk I was talking about. The piece of string on this side pulls that way. The piece of string on the other side pulls that way. We resolve that into components. The hypotenuse is the string tension F. Hypotenuse times the sine of the angle would be the opposite side, which is the downward pulling component. Well, this angle would actually be very small, a small fraction of a degree probably, because this is just a little tiny, basically a little differential size piece of the string we're talking about here. And for small angles, sine theta is approximately equal to theta in radians. So we've got a downward component on this end of our little piece that's equal to F times theta, and a downward component on the other end also equal to F times theta. So altogether, 2F theta pulling downward, and I'll write all that out in a moment. And I'll also hang the camera on something where it's not jiggling around on you like this. But I've got a few more things to point out on here. If we're going to say this is a small circular arc, then, well, if theta is the angle to the middle there, S equals R theta from, I think that was section 7, is the length of this part. Same thing over here. So the total length of it is 2 times R times theta, where theta is the angle that the string tension is below horizontal. See, if this is theta, and if you've got 90 degrees here, because the string lies along a tangent to this little circular arc, the string tension pulls along a tangent, and a tangent is perpendicular to a radius. So if this is 90 degrees, theta here, 90 minus theta over here, so it's theta over here. Anyhow, 2 times S equals R theta gives 2 times R theta for the total length of this piece, and that's something we're going to need to keep in mind. And as I said, you're running alongside of this, so it looks to you as if the string is moving to the left. To the string, it looks to you, it looks to the string like you're running to the right with a speed v, but it looks to you as if the string is moving to the left with a speed v, and I think that's the introductory stuff I need to point out. So let's see if I can get this hung up without jiggling you around for too terribly long. Let's see if I got that straight. Maybe a little higher, kind of like that. That'll be good. Okay. So, speed of waves on strings, transverse waves on strings. A string wave. One thing that we're going to need to make use of is what's called the linear mass density. Which is going to be represented by the Greek letter mu. I guess I could aim that a little higher still. Yeah, right around there is good. So, you see, I'm going to need, ultimately I'm going to use the formula for centripetal force, mv squared over r. I need something to put in for the mass, m. And that's where this is leading to. The mass of that little piece I was showing you would equal its mass per unit length the mass of that little piece is its mass per unit length times its length. Well, the mass per unit length is this symbol I just wrote down, the Greek letter mu. And as I was explaining when I was pointing the camera at the note packet, the length of the little piece under consideration is 2 times r times theta. If you didn't quite get that as it was going by, that's the beauty of video recorded lectures. You can rewind it and listen to it again. But that's from applying S equals r theta to each of those two halves that was shown there. So now let's do it this way. Summation of the forces in the y direction equals it's Newton's second law, okay? Summation of the forces in the y direction is equal to the mass times the y component of the acceleration of that little chunk of the string. And if it's in uniform circular motion, its acceleration is equal to v squared over r. More review from earlier in the course. So I've got this, well, first of all, for the force. Remember I was pointing at maybe I should draw a sketch here. There was the little piece of string like that, and the adjacent pieces of string pulled down like that. We had a downward force, a downward component there, and a downward component there, and they were each approximately equal to f times theta. Actually f sine theta, but I was making the small angle approximation of sine theta equals theta. So the total force pulling downward toward the center of curvature of this little piece is 2 times f times theta. I keep sliding my paper up. Either that or maybe you know what I think? No, the camera's not drooping. It's just, anyhow, mass from over here is mu times 2 r theta, and then times v squared over r. Well, then we have a flurry of cancellations that go on. The 2 cancels the 2, and the theta cancels the theta, and then we've got an r over r here, so we'll cross them out also. And what's left is F. F, once again, is the tension in the string, okay? The tension in the string is basically the force that pulls the wave along it. The harder, the more force, the harder it pulls the wave, the faster it moves. That'll show up when I'm done here. But we've got, all that's left is mu times v squared. So therefore, F over mu equals v squared, which tells us that the speed of transverse waves on a string is equal to the square root of F over mu. And in a moment, you'll be switching back to my slightly younger self standing in front of a chalkboard, and that'll be written on it. But I'll probably mention this again in the older recording, but basically what's going on here is, as I said just a moment ago, more tension gives you a faster speed because, bigger force pulls harder on the wave, basically, to oversimplify things a little bit. We've got an inverse relationship. I wouldn't exactly call it an inverse proportion because there's this square root in between. But there's a sort of an inverse relationship between the speed and how heavy the string is, mass per unit length. Well, more mass means more inertia. More inertia means it behaves more sluggishly, which slows the wave down. And that is where we can leave this off and go back to the other recording. Alt R.
So the speed of waves on strings is equal to the square root of F here, the capital F is F for force. That's the tension in the string. Mu is the linear mass density. So for example, let's say you're tuning your guitar, okay? And plink, 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 plink. That sounds a little flat. What do you do to, you see, the frequency, little f for frequency, the frequency of the waves traveling along that guitar string, which equals the frequency of the sound it produces when it vibrates. Frequency depends on the speed of the waves and also the wavelength of the waves. Well, the wavelength is determined by the length of the string. You change that by putting your finger on the string and pinching off part of it to make it shorter, okay? But aside from that, for a string of given length, if it's maybe not quite the frequency it should be, you can change the speed of the waves by adjusting the tension on it. A guitar has those tuning pegs up at the top of it, and you crank on that a little bit, and that pulls tighter. A higher tension equals a higher speed. A higher speed gives you a higher frequency, and so you tune the thing that way, okay? The other factor that determines the speed of the waves on your guitar string is how heavy the string is. If you look at it, I mean, some of you are musicians and some of you aren't, but if you ever get a chance to take a good look at a guitar, you'll see that the higher notes are just a bare piece of wire, whereas the strings for the lower notes have a second piece of wire wound on top of the first one to make it heavier. Okay, it's even more dramatic if you've ever seen the inside of a piano. You open that up and look at the strings. The high notes over on the right-hand end, of course, those strings are shorter also. That determines the wavelength. But aside from the differences in length, over on the high note end, you've got just the bare piece of wire. In the middle of the piano, there's that second piece of wire wound on top of it to make it heavier. Down on the low note end, there's a third piece of wire wound over the top of that second one. Big fat strings down there. They call them strings even though they're really wire. And you see, more mass equals more inertia. More inertia slows the waves down. So bigger mass per unit length, smaller speed. The string tension is the force that pulls the wave along the string. Pull harder, waves go faster. Okay, so the tension is used in tuning, not only guitars, but that's how you tune a piano. If you've ever seen how it's done, there's a peg and they put kind of like a wrench on there and adjust the tension. Tension is used to adjust, to tune the thing. The effect of the mass per unit length is used in how the instrument is constructed in the first place. And then the length of the string affects the wavelength. So, you put your finger on the string and that gives you a higher note than when you take your finger off of it. Physics is everywhere. Looks like I'm on speed of sound now. Yeah, all it says on the handout here is there's just a little line that says speed of sound. And I guess we'll go back over here. I'm just going to write down a formula. Now, if you want to talk about the speed of sound in general, a formula that will give you the speed of sound in air or the speed of sound in water or the speed of sound in helium. That formula actually looks pretty similar to the one that I just wrote down for the speed of waves on a string. Once again, it's got a square root in it. Once again, there's a fraction inside that square root, and on the bottom of it is the density. Sound moves through 3 dimensions rather than along a 1-dimensional string, so instead of mass per unit length, you'd be talking about the mass per unit volume. Up in the top of the fraction where the string tension is, well, that part's a little different. It's a property of the medium called its bulk modulus, which is a measure of how difficult it is to compress it. Okay, is it squishy like air, or is it incompressible like water, and just how incompressible is it? But anyhow, I'm just kind of throwing that in as a little footnote. The only thing we're going to worry about officially in this course is the speed of sound in air. Speed of sound in air. And if you're interested in a more complete and general description of the speed of sound, I will refer you to the textbook, because that formula I was just describing is in there, and it shows how to derive it and everything. At least I think it shows how to derive it. If it's a good textbook, it ought to. But if you plug in the appropriate values for the bulk modulus of air and the density of air, well, you're left with something that's a function of the temperature. The density, for example, air tends to expand as you get it hotter, and I believe the bulk modulus is also a function of the temperature. So what you end up with plugging in the appropriate properties of this particular substance, air. It's the square root of 402. This is assuming that this is going to be in meters per second. Of course, it'd be an entirely different number if you're doing feet per second or miles per hour or something. But 402 times the absolute temperature. You want Kelvin, not Celsius. You have to count all the thermal energy that's there, not just the part that's above the freezing point of water. Somebody slips you degrees Celsius, which is pretty common. Most thermometers read Celsius, not Kelvin. You have to add 273. And that formula is on the formula sheet, and that's really about all I'm going to say about that. And then it says, yeah, I think I should slide you back over here and wave my hand around trying to make it focus again. It's got to go up a little higher too. That seems to be okay. So the speed of light. This will be the shortest discussion of all. I mean, I kind of abbreviated talking about the speed of sound and says don't worry about anything except the speed of sound in air. But the speed of light in a vacuum, it's just a number. It's not even a formula. Okay, the speed of light in free space turns out to be a universal constant. It's like the gas law constant or the gravitation constant or any one of those. It's always the same thing, no matter what's going on or where you are. It's actually just a little under 3.00 times 10 to the 8th. But if you round it off to three significant figures, 3 times 10 to the 8th. This is if it's moving through a vacuum. If it's moving through some material substance, like water or glass or something like that, the story becomes significantly more complicated. And this seems to be my day to talk about physics 133. More detail on electromagnetic waves is, there's a whole week. I think it's section, it's toward the end of the course. It's like section 10 or 11. But there's some place in physics 133 where I spend a week talking about electromagnetic waves. And we'll get into that there if any of you take the third course. But for purposes of physics 131, we will stick to either the speed of light in air is only very slightly slower than the speed of light in a vacuum. If you're rounding things off to three significant figures, this would also be the speed of light in air. And for purposes of this course, we'll just leave it at that. Now, this is not only the speed of visible light, but visible light turns out to be just one fairly small part of a much larger spectrum whose main parts I've listed out here. All of these different types of radiations, which you might have thought of as being different things, are really the same thing. They're all, in a sense, light. They're just types of light that your eyes don't happen to respond to. And actually, the visible part of the spectrum is quite a small part of this. From the longest wavelength you can see, which would be the red end of the spectrum. The border between red and infrared is the long wavelength end. From there to the short wavelength end of the spectrum, where violet borders up against ultraviolet, the difference in the wavelength and also the frequency is only approximately a factor of 2. If you go to one extreme on the radio end of the spectrum, you could have a wavelength that's the size of the Earth, you know, the diameter of an Earth. You get down around, I don't know, 10 or 20 hertz or something like that for the frequency, and you're talking about thousands of miles for the wavelength. At the other end of the spectrum, you get way down into the gamma ray part of the spectrum, good hard gamma rays, and you're talking about a wavelength that's the size of an atomic nucleus, something like 10 to the minus 15 of a meter. And so this mechanism, which will be described in the third course, that electromagnetic waves propagate with, that works over an extremely wide range of frequencies and wavelengths, of which your eyes are only sensitive to a fairly narrow part, just a factor of 2. But we take that one small part of the spectrum and divide it up even further into the colors of the rainbow. And remember the name of this person who never actually existed at all, Roy G. Biv. Might be fun to go to a bank and open a checking account in his name, or try and get him a social security number or something like that. But what it stands for is red, orange, yellow, green, blue, indigo, which is kind of a purpley bluey color, I guess. I've always been suspicious somebody just made up that color to put a vowel in Biv. Because I don't know about you, but when I was in kindergarten, there was no crayon in the box that said indigo. There was purple and there was blue, but I don't remember any indigo. Anyhow, blue, indigo, violet. Roy G. Biv helps you remember the colors of the rainbow in order from the long wavelength end to the short wavelength end. And it's good for you to be kind of familiar with the electromagnetic spectrum. Maybe one little comment I'll throw in here is it's the short wavelength end, the high frequency end of the spectrum, which is bad for you, okay? Ultraviolet radiation can't penetrate into you any deeper than skin deep. So it'll only give you skin cancer. You get down into X-rays and gamma rays, those things can go right through your body and out the other side. And so that can give you cancer anywhere. On the other hand, things like microwaves are usually, I mean, there's always a few people who are kind of outliers and have unusual opinions, but conventional wisdom anyhow is that the stuff at this end of the spectrum is not harmful unless you're talking about high enough intensities to cause significant heating, okay? Your body is quite sensitive to just minor changes in its temperature. It's like normal body temperature is around 98 or 99 degrees Fahrenheit. And I think you only have to get up around, you know, for a fever, you only have to get up around 106 or 107 or something like that. I'd have to look it up to see for sure. But, you know, if your body temperature goes up just 10 degrees Fahrenheit, that'll kill you. And so, you know, if you put a mouse in a microwave oven, well, let's just say don't put a mouse in a microwave oven, okay? But as long as it's not intense enough, as long as the waves don't have a big enough amplitude to cause significant heating, a little bit of microwaves or infrared is generally not thought of as dangerous. So let's see. we have a short example for me to run through. So as I was saying earlier, the way you tune a musical, well, string musical instrument, the way you tune it is by adjusting the tension on it. And let's say that the piano tuner has come and the particular string that the tuner is working on right now, the proper speed for the waves is 240 meters per second. If the waves that are reflecting back and forth going up and down that string, if they travel at that speed, then it will vibrate at the correct frequency for the note you're trying to produce. It gives the mass per unit length. And the question is just how many newtons worth of tension should this string be under? So the way we're going to do this is, remember this thing back here? Question tells me V. Question tells me mu. F is what it asks for. What more could you ask for in terms of an easy problem? Well, I guess what more you could ask for is that mu be in the correct units. We do have to move the decimal point, but aside from that one little detail, it's pretty much a plug and chug, very straightforward kind of. V equals the square root of F over mu. Some textbooks use T for tension instead of F for force, but we're going with F. That implies, mathematical symbol for implies, square both sides, then multiply both sides by mu to solve it for F. Just drop in the numbers. So you move the decimal 3 places to convert grams to kilograms, stick it in the formula, punch it up. 202 newtons, which is like around, give or take, something like 45, 47 pounds, somewhere in that neighborhood, I believe. And that's just one string, okay? There are a lot of strings in a piano. And if you add up the tension on all of them, the total is several tons, trying to, make the piano collapse, which is why you need such a strong frame around the strings, which is usually, I suppose if it's an old enough piano, it might be cast iron. I would imagine they'd probably use steel in a new piano. But either way, that makes the thing heavy. If you've ever, the two worst things to move are pianos and refrigerators. And the fact that you need a strong structure to stand up to all that tension, that's kind of what makes, or at least part of what makes pianos so heavy. Next thing on the handout, I'm not going to point it at the thing just for you to see the word intensity and bring it back. I'm just going to write down the word intensity. The intensity of a wave is defined like this. I'm assuming here now a wave that's propagating in 3 dimensions, like light moving away from a light bulb or sound moving away from me as I stand here talking about it. So as the waves radiate outward, how much power passes through a given area? The area is assumed to be perpendicular to the direction of propagation of the wave. So if we're talking about the sound waves coming from me, they're traveling along like that, you'd want to be talking about an area oriented this way, perpendicular to the direction the waves are moving. Power is measured in watts, area is measured in square meters. So it's describing the energy carried by the wave. How many watts per square meter, how concentrated in terms of the area that the wave passes through, how concentrated is the energy in the wave. Now, I'm just going to mention something briefly in passing that I could manage to make much longer if I had the time to do that. I'm just going to kind of put in parentheses for any wave, whether it's light or sound or anything like that, any wave propagating in 3 dimensions. Today's arcane mathematical symbol, proportional to. For any kind of wave, the intensity is proportional to the square of the amplitude. When I go over electromagnetic waves in Physics 133, we'll see the details of that for the case of light. We don't really get into it anywhere for sound or seismic waves or anything like that. But in general, if it's moving through 3 dimensions, that's the case. So in other words, this gives us an alternate way of describing the loudness of sound or the brightness of light. I had said earlier that amplitude corresponds to loudness or brightness. Waves with larger amplitudes carry more energy. If you've got a dock on the ocean and it's just a nice day and you're sitting there dabbling your toes in the water and there's these cute little waves going by, well, they don't carry much energy. But when the hurricane comes and now it's 15-foot waves, now you don't have a dock anymore, you've got a big pile of toothpicks. So the greater the amplitude, the more energy is carried by the wave. So this is kind of how it works. Intensity is the energy per unit area. Bigger amplitude means a higher intensity. Now, the next thing it says there is how intensity varies with distance. And again, we're assuming here a wave moving in 3 dimensions. Water waves that move in 2 dimensions would be somewhat different. But let's say you've got a light bulb right there. Or if it's sound, it could be a loudspeaker or, whatever. Waves propagate away from that source in all directions. let's say you wanted to know what is the intent. I'm assuming here that, the simplest case is that if the source is broadcasting the waves evenly in all directions. So no matter what direction the wave is going in, it's got the same amplitude as the waves going in any other direction. As usual, we could make the argument more complicated for a more general case, but just looking at the simplest case to kind of illustrate the point. What if I want to know the intensity a certain distance from the source, 1 meter away or something like that? Well, imagine a sphere of radius r around that source, okay? Just an imaginary surface, something you're picturing in your mind. As the waves travel outward, they pass through this imaginary surface. If you want to know how many watts per square meter the wave has at that distance, the question is, how many square meters are there for the wave to pass through at that distance? Well, the collection of points that are at that distance from the source would be a sphere. So what's the number of square meters at a distance r? Take the wattage and divide it by that many square meters, and that would be the intensity that you have at that distance. So intensity is the power now when you call something a 60-watt light bulb, that's the amount of power that it takes in from the electric current. A significant part of that is actually given off as heat rather than light, especially if it's one of the old style incandescent bulbs. But even to some extent with the modern ones, I'm talking here about how many watts are actually given off in the form of light. Okay, so how many watts do the waves carry? And power per unit area, the area of a sphere, and if you ever need to know this, which you might someday, not right away, but there will be times in the spring semester, you can look this kind of thing up on the formula sheet. Remember, some of the pages toward the back are mathematical background, and you can look up things like the quadratic formula and things like that there. Well, among the stuff that I have in that part of the formula sheet is some geometric formulas, including this one. So surface area of a sphere at a distance r from the source, the watts from the source are distributed over an area of 4 pi r squared, which shows you that the intensity is inversely proportional to the square of the distance, okay? If you go twice as far from the light bulb, you will have 1/4 of the intensity. 3 times as far away, and you've got 1/9 of the intensity, and so on. Actually, it's not just waves that work this way. As we'll see in the case of gravity, pretty soon, actually, I think that's the next unit in the course, the strength of a gravitational or electric field drops off as the inverse square. Anything that propagates outward in 3 dimensions like that is going to be an inverse square law, whether it's some kind of wave or whether it's electric flux or the strength of a gravitational field or anything else. They're all inverse square laws for basically the same reason. Maybe a little handier way of putting that inverse square relationship would be if you want to compare 2 different distances. So here's the source once again. Maybe instead of a light bulb that's on continuously, maybe it would be helpful to picture some sort of a flash bulb going off, like the flash on a camera, except there's no reflector behind it. You've just got a bulb out in the open that's going to throw light in all directions. So the thing very briefly flashes. This creates a bubble of light that will expand around the source. At one particular instant, the radius of that bubble of light is R1. And you know, if a light bulb is on continuously, you can just think of that as being a whole bunch of these bubbles nested inside each other. But anyhow, it's this big at a certain time. A little while later, it's gotten to R2. So the energy that used to be spread across this smaller area a short time later is now spread across this larger area. Since energy, you know, power is energy per unit time per unit area. So because of conservation of energy, you have to have the same power, the same energy per unit time flowing through both of these imaginary spheres. If I is equal to the power over the area, the power equals I times the area. Multiply both sides by the area, and the power would be because of conservation of energy, the power that goes through the one sphere has to equal the power flowing through the other sphere. You can divide through by 4 pi, get rid of those, and do a little more algebra. And there's the, like I was saying, you know, when I was talking about this back here, it's an inverse square relationship. If you're comparing two different distances, 3 times the distance means 1/9 of the intensity. So that's why if you're walking down the road away from a street light, that's why the light level gets dimmer and dimmer and dimmer, because at greater distances, the power coming from the street light gets spread out over larger and larger areas, reducing the intensity. And the next thing it says, eventually I'll point you at that again. There's an example coming up before too long. But the next thing is just 3 words. It says the decibel scale on the handout there. So the loudness of sound, I mean, the brightness of light sometimes is described by its intensity. Anybody who knows anything about solar astronomy can tell you right off the top of your head, or of their head, that the intensity of solar radiation at the top of Earth's atmosphere is 1,340 watts per square meter. Or sometimes you'll hear 1,360. As with many experimentally measured things, it's slightly different depending on who did the measuring. But sometimes the brightness of light is described by its intensity. In principle, you could describe the loudness of sound that way. The problem is just that you're dealing with such a wide range of numbers, from the faintest sound that you can just barely hear to the loudest sound that you can just barely stand, you're talking about roughly 12 orders of magnitude. So if you were writing down intensities for different sounds, you'd always be counting all these dumb zeros, or at the least you'd have to be using scientific notation all the time. It seems so much more convenient to have a more compact range of numbers than, you know, some numbers that are 1 trillion times bigger than others. This is one of the reasons for using a scale based on the logarithm of the intensity rather than the intensity itself. Another reason for doing it that way is a logarithmic scale actually comes a little closer to the actual perceived loudness, which is not exactly logarithmic, but it's closer than just talking about the intensity. If you compare a sound whose intensity is 10 to the minus 6 watts per square meter to a sound whose intensity is 10 to the minus 3 watts per square meter, that second one does not sound anywhere near 1,000 times louder, even though it's got 1,000 times the intensity. So for a couple of reasons, a scale based on the logarithm is a little more useful. The threshold of hearing, which you can just barely make out if there's no louder sounds to drown it out, and if you've got ears that are in good condition, a young person with good hearing, which is not actually something I qualify as anymore, but around 10 to the minus 12 watts per square meter. The threshold of pain is somewhere roughly around 1 watt per square meter. So 12 orders of magnitude. The unit based on the logarithm is called a bell, after Alexander Graham Bell. I'm not quite sure why it's spelled with only one L when Bell spelled his name with 2. It's these sorts of things have happened more than once. I mean, with Michael Faraday, they dropped several letters off the end of his name when they named a farad after them, which is the unit you measure capacitance in. But anyhow, for whatever reason, a bell with one L. That would give you a scale that goes from 0 to 12. Well, that's kind of overshooting. That's a pretty rough thing. So what's more common is to measure in decibels instead. Deci being one of those metric prefixes, 10 decibels to the bell. So the formula that goes with this sound level, that's not very good, E. The sound level in decibels, we'll use the Greek letter beta to represent that. So 10 to the minus 12 watts per square meter, an arbitrarily chosen reference intensity, chosen because it's been experimentally determined to be approximately the threshold of hearing, minimum loudness that you can hear under optimum conditions. So the intensity of the sound you're listening to, you form the ratio of that intensity to this reference intensity. You take the logarithm of that. This is a common log, by the way, a log to the base 10. Usually when you're describing nature, you're using natural logs, but this is not describing nature. This is just some definition somebody made up one day, and so it uses a common log. So the logarithm of that ratio ratio is called a bell. You put the 10 on there, and that makes it decibels. So the way this works is if the threshold of hearing is around 10 to the minus 12, you'd be taking the log of 1, which gives you 0 decibels. Now, in principle, still fainter sounds could exist, which would give you a negative number of decibels. In practice, first of all, you can't hear anything that faint. And even if you could, in practice, there's always some louder sound around to drown it out anyhow. So you don't really come across negative numbers of decibels, even though in principle it could happen. So 0 decibels at the threshold of hearing. The way a logarithmic scale works is every time you multiply the intensity by 10, you add 10 to the number of decibels, okay? So for example, if you compare 50 decibels to 100 decibels, as far as the amount of energy your ear is absorbing every second, intensity is energy per unit time per unit area. 50 decibels compared to 100 decibels, your ear is not absorbing twice as much energy per second. Your ear is absorbing 100,000 times as much energy per second, okay? Every time you multiply the intensity by 10, you add 10 to the number of decibels. 50 decibels is just, a few little examples. 50 decibels might be about right for a fairly quiet conversation, like, when you're sitting in the library and you're talking to your friend sitting next to you in the library, and you don't want the librarian to come over and quietly yell at you. That would be around 50 decibels. 90 decibels is the maximum considered safe by the Occupational and Safety, OSHA, Occupational Safety and Health Administration. If your job is to sit next to a machine all day, every day, and it will expose you to 90 decibels, you're required by law to have hearing protectors, either headphones or earplugs or something. There's another agency, the National Institute for Occupational Safety. They set the limit at 85 instead of 90. You might get 100 decibels from a power mower. When I was a boy, we had this old lawn tractor that the muffler had rusted off of, and every time I mowed the lawn, I noticed my ears were ringing when I finished and got off of it and turned it off. In hindsight, might not have been a good idea. But 115 decibels is where it's illegal to expose a worker at all, like 1 second. 115 decibels, you're supposed to have the headphones on. 115 decibels is also not unknown at a concert. It's not a workplace. OSHA standards don't apply. They have no jurisdiction. Somewhere around 120 decibels or maybe a little more is the threshold of pain. That's where you start getting uncomfortable and wanting to put your hands over your ears. I don't have it written down, but I have the idea that ground zero when an atomic bomb goes off is 200 and some decibels. Not sure exactly, but anyhow, time for me to do a problem. Back there. It's only a line and a half. Let me just read it to you. It says, a certain distance from a siren, the sound level is 70 decibels. What is the sound level if a second identical siren in other words, your house just happens to be halfway between two fire stations with identical sirens on them. And the siren goes off at the one fire station, and at your house, that creates 70 decibels. Well, a few minutes later, the siren goes off at the other fire station. How many decibels do you have then? Your first impulse might be to say, well, that's going to double the loudness if it's two sirens, so 140 decibels, right? No, not even close, sorry. The thing that gets doubled is the intensity, not the number of decibels. Each siren throws a certain amount of energy into the air per second. And so it's the intensity that involves energy per unit time per unit area. So we have to figure out the corresponding intensity, or do we? The intensity that you get from two sirens will be 2 times the intensity that you get from one siren. So it's the intensity that doubles. So we know that I1 corresponds to 70 decibels. I'm going to put that into this formula here. "70 decibels corresponds to the original intensity, I1. The new level how many decibels do we have after the second siren comes on? Same formula. The number of decibels I'm looking for corresponds to I2, which I just got done saying is equal to 2 times I1. Now, probably the way most people would go after this is they would take this first equation, run through several lines of algebra to solve it for I1, and then take that number and stick it in here to calculate the answer, and that'll work. Perfectly good way to do it in terms of getting the right answer, but if you are clever, there is a quicker and slicker way to get through the math. I've made use of a well-known property of logarithms. And if you don't quite know the well-known property of logarithms, that's another thing you can find on the later pages of your reference handout, but it's this one. After I write it down, maybe it'll look kind of familiar from some intermediate algebra class you hopefully took. For any kind of logarithm, whether it's a common log or a natural log or a log to the base 12.5, which probably nobody has ever used in the history of mathematics, but whatever kind of log it is, the log of a product is the sum of the logs. Log of A times B equals the log of A plus the log of B. Sound kind of familiar-ish, I hope? Well, if it doesn't, I just told you. And if anybody really wants me to see me do it, let me know. I can prove it to you in about 2 minutes. But what I did here is I said, I've got the log of 2 times everything else. The log of 2 times everything else would equal the log of 2 plus the log of everything else. And the reason that I shouldn't have written that there, it's right in the way, but the reason I wanted to divide things up like that is the second term maybe seems kind of familiar because it's exactly what I wrote back over here. I've got a thing written over there on my left that says this is equal to 70 decibels. And get out my calculator and punch this up. Close enough, you might as well call it 3. 70 plus 3, 73. Anytime you double the intensity, it's going to add 3 decibels. Because that's what logarithms do. Well, I think I'm going to, I've got time. Yeah, maybe I'll just break off between topics. I'm not going to fit quite all of section 11 into one recording, I don't think. Well, we'll see what time it is when I finish this next example, but there may be a short third recording that's like 20 minutes long or something like that, but definitely have time to do one more of these. Focus. Okay, number 5, 25 meters from a machine in an open field. The reason I made it an open field is so that the sound would spread out in all directions, like I was assuming when I talked. I'm going to be using the inverse square law in this one, and that's based on the assumption that the sound spread out in 3 dimensions. Like, for example, if you talk into one end of a piece of pipe, some tube with nice hard walls, that pipe could be 100 feet long, and somebody with their ear to the other end of that pipe will hear you just like you're standing next to them. I mean, that's how they used to communicate in ships years ago. before they had any kind of electronic way of communicating. They had a tube that went up to the bridge, and the other end went down to the engine room, and it's like, okay, full speed ahead, and the guy down in the engine room's got his ear at the end of the tube, and he yells to the guy that's shoveling the coal, full speed ahead. So if you don't let the sound waves spread out, then the intensity does not drop off with distance. Or even if you kind of restrict how they spread out. I mean, I've got decibel meters, and if you tried to do a lab with the inverse square law in this room, you would find that it abated fairly close, or fairly well close to the sound source. Maybe I've got a loudspeaker going, and for the first meter or so, right up close to that speaker, it would work pretty well. But then it's going to even out, because you're picking up sound that not only comes directly from the source, but you're also getting reflections off the floor and the walls and the furniture and all of that. And by the time you get to the back of the room, it's going to be pretty much the same number of decibels everywhere. Anyhow, that's why I made it an open field, because that makes the inverse square law valid. And so you're walking away from this machine. Somebody's left a tractor sitting there running in the middle of this field. 25 meters away, 80 decibels. This may be a tractor that does not have a particularly good muffler on it. May not have any muffler at all, in fact. But anyhow, you're walking away from it, and when you're 40 meters away, what's the number of decibels there? Well, again, you've got the intensity, you've got an I1 and an I2. In the previous example, that represented the intensity at two different times. Now it's going to be the intensity at two different places. And the question says that you've got 80 decibels. You've got 80 decibels at the first place. That would be when you're 25 meters away. So I'll take that 80 decibels and stick it in the formula from over there on the other end of the blackboard. The important point here is it's not the decibel level that obeys the inverse square law. It's the intensity. It's the watts per square meter that drop off as the inverse square of the distance. So I'm going to figure out how many watts per square meter this is. Stick that into the inverse square law. And then finally, last step, how many decibels corresponds to that many watts per square meter. So that's the strategy here. Running through the details, and there might be some clever way of manipulating the logarithms. In this case, I don't know. It probably wouldn't help you as much as it did in number 4. So I'm just going to do it, get a number for I and do it that way. To solve this for I, well, the way you solve any equation is you peel stuff away from your variable in layers until you take it down to where it just says I equals, or X equals, whatever the name of your variable is. The outermost layer here is that 10. To get that off of there, divide both sides by 10. Next layer. What is the outermost layer around our variable now is this log. The way you get rid of a function is to hit it with its inverse function. The inverse of a logarithm is an exponential. In this case, because it's log to the base 10, it would be 10 to the x. If it was a natural log, you would do e to the x, okay? So 10 to both sides. Inverse functions cancel each other out, like taking the square root of a square or the arc sine of a sine. Inverse functions cancel each other out. So the exponential and the log kill each other off, and what you're left with is just the I1 over 10 to the negative 12. All that's left now to solve it for I is to get that denominator out from under there. So multiply both sides by 10 to the negative 12. If you want to say it in proper scientific notation, I guess it would be 1 times 10 to the negative 4. But that's the intensity that corresponds to 80 decibels. That decreases as the inverse square of the distance while you're walking away from this machine. From a page or so back in your notes, maybe half hour ago in this same recording, I said I2 over I1 equals R1 squared over R2 squared, and I've just done a little bit of minor algebra to solve it for the thing I want to know, which is I2. Fill in the numbers. I just got done determining that I1 is 10 to the minus 4 watts per square meter. Fill in R1 and R2. Here is a point where I sometimes see people make a mistake. And I guess I could say the same thing about almost any kind of problem. You should be trying to keep in mind, does what I'm getting make sense? Okay. Physical intuition is really helpful. If you're walking away from the machine, the sound should be getting fainter. I2 should be smaller than I1. If your calculations are telling you that walking away makes the sound get louder, you have almost certainly switched R1 and R2. Be alert for that kind of thing. Because I have more than once used red ink for that. So you calculate all this, it comes out 3.91 times 10 to the negative 5th. Finally, the number of decibels that corresponds to that. few more buttons. 75.9. And the last topic in section 11 is the Doppler effect. And that's going to take just a little more time than I want to spend right now. So I think I'll pause here and make a third recording because the first one was a little on the short side. And of course, the temptation is always to say, I'll see you then, but I'm not going to see anybody. I'm going to be talking to an empty room some more. But you'll see me then. Goodbye until then.